Thank you everyone for being here. So yeah, today I'm going to talk about a new regularization method for the learning of kernels in operators. This is joint work with my two students, Chen Junnao and Chen An, and they will be on job market this fall. And yeah, if you have any positions, that'd be great. And first, I would like to thank the support from Johns Hopkins and the Natural Science Foundation. Okay. So in this talk, I will have 4 sections here. On top, we can see here. The first section is learning kernels. Second one is the classical method of regularization and further regression. And the third part is the main part of this talk. I will talk about the identifiability issue and the regularization method data. And in the last part, I will show some numerical results and also explain, summarize the results in the end, the future work in the end. Okay, so to begin, we are going to first state what the problem here we're considering, which is the learning kernels in operator problem. So what we consider here is we want to learn the kernel phi in this operator R phi. R phi acts on U and then give us F. So here then we have observation noise in F, basically in the observation part, not in the variable as Ravi just talked. And the data we have is data pair of UK and FK. And here, UK and FK are functions with their function space to be specified. And in this talk, mostly the F will be in L to omega, which omega is the space, function space, a domain in Rn. And in this case, in our example, I will just study the 1D, but the theory applies for general. And then the space X depend on the operator itself. And the operator are in the following, in the following forms. First, the operator can be either linear or non-linear in U, but the thing here is it's linear in phi in the kernel we want to learn. Okay, the example of such kernels are first is the long local interaction kernel in the interning particle system. The equation here we have is the mean field equation of the first order interaction particle system with white noise environment, where the sigma is the white noise part, and then the interaction part comes from the drift part give us this part of the interaction. And it's called aggregation part. And this is the divergence of the solution U, and then K phi convolute with U. And K phi is defined as follows. So the kernel here is radial, and then the X in RD is the direction of the interaction between with the other particles, and the phi X is the strength of influence. And then we can also study this long local PD operator or fractional diffusion operator. For example, the long local PD operator is in this format. It acts on U with the Uy minus Ux globally integrated with the kernel phi. So this is different from the classical local operator or derivative operator in the sense that classical one depends on this X and very near of X, and then they take the derivative. Here it's kind of integration over all the range of omega. Okay, and when we have the second order in time here, we have wave propagation problem. And that's the long local PD operator or fractional diffusion of this first part. And similarly, from this one and this one, we can see here a common part is that we have an integral with respect to kernel phi. So then generally other operators including integral operators, and then since we can integral operators, we will also have deconvolution, because all these two parts can be viewed as convolution, deconvolution operators, and can be also viewed in this way. And we also have the tuples and Hankel matrix also have a kernel. We can also recover this kind of kernel. So here, this space can be either function space or high dimensional vector space. Okay. So that's the operator. And then for the data, there are 2 types of data. And the main feature here is that data for the function part, it can be discrete and noisy. And its main point is that data have long local dependence on the kernel to be learned, because here it have the integration with respect to the kernel. Okay. And there are 2 types of kernel data. The first type of data is that the data UK and FK are both random, and they are sampled from the joint distribution in the function space. So this is the statistical learning problem. And another setting here is that we have very few data, very limited data, like only 1 pair of data or a few pair of data. So in this case, it's more like a deterministic inverse problem. So in this talk, I will focus on this deterministic inverse problem setting, which is easier, and we will see that the connection to this potential generalization to the static learning That's the future research. Okay, before we move on to the algorithm learning of this kernel, let's first compare these with classical learning to see where we are and how does this relate to other learning problems. It's like Ravi mentioned for the operator learning. Okay. So then in the classical learning, we have xi, yi. We want to learn the function y equal to phi x. And in this case, we see here, this value here, yi, is the local perturbation. This epsilon is a white noise or some other noise, is a local perturbation of this phi value here. Like what do we have here? So the phi value here, we add a noise, is just local perturbation of the value phi x. And in this case, we can view this classical learning as an interpolation problem. And we can have the function here. For when we are learning kernel phi in an operator, as we know, the data depend on the phi locally. In this case, given this function data, we have little information about what the value of phi could be. So the values of this function is underdetermined from data. Okay, that's the key thing, is the long local dependence. And another direction here is we are essentially learning the a function parameter in the operator phi, and then we can view this as an operator learning problem. In this case, if you look at the operator learning, and then the goal here is learn this operator without worrying about the phi here. And then in this case, we can view this as this axis as the U, infinite dimensional function, and then we can learn approximately the operator. So we can still view this as a local perturbation problem. And then we still have local dependence. So this one is much more hard than the classical regression function or learning function because the dimension is much higher. But at the local dependence point of view, the classical learning and the operator learning are similar. Okay. And comparing with operator learning, what we have learning kernel is that we assume a low dimensional structure phi here, while the operator learning does not really recover this phi. They don't assume this low dimensional structure. So that's the difference. Okay. With this one, we see that when we learn this function phi, and then we can compare with the classical learning algorithm, basically we can use different type of methods, in particular regression methods or machine learning deep learning methods. And in this talk, I'm going to focus on the low dimensional phi because we focus on the low dimensional structure of the operator. So I will consider basically radio kernel or just 1D kernel. In this case, we're going to focus on regression methods. But in the process of formulating regression methods, we are going to use the minimizing the loss function point of view. And so these theory developed later can also hopefully be generalized to neural network approximation in the machine learning or deep learning methods. Okay, so to be more specific, our setting will be, we will consider the deterministic inverse problem, and we have the function data are as discrete mesh. Here, xj is the spatial mesh, a discrete mesh. And we're going to consider first in a dimension 1. In this case, the x is just a uniform mesh we want to study. Okay. And now we come to the method. Since our goal here is to learn a 1D function, and we're going to try to use the regression method, non-parametric regression method. Another key point here, we want to use non-parametric regression is natural because we have little information about what the function phi should be. So non-parametric regression is the first choice. And first, we'll minimize find the loss function. In this case, we want to minimize the mean square error on both sides of the operator. And then in this case, we assume f is in L2, we use L2 norm. But if you have other norm, we can also use other norm. And in this formulation, we have loss function, a goal here to minimize it. So when phi is high dimensional, is an independent variable is high dimensional, we can also use neural network approximation. But in the following, again, we focus on 1D. Okay. So in this case, we're going to use regression. And the key point here is this R phi depends on phi linearly. So our loss function here, because the square here, is quadratic. So in the regression point of view, we just pick a hypothesis space with an basis function phi I and n to n the dimension. And then what we need to do is find the coefficient di. And since phi is quadratic, we can always write it in the quadratic form. And then everything reduced to the find the least square or the inverse b problem. Okay, so that's the regression point of view. And then for the non-parametric regression, there are three issues to be addressed. First, we are doing the inverse. And in general, we could use the pseudo inverse if Bn doesn't have error. But in our case, as we see, we have the noise error or numerical error. So in this case, if B is if AN here is ill conditioned, the problem is likely we need regularization. And in general, that means we should study whether this AN is well conditioned or not. In other words, if the inverse problem is well posed or not. And also similarly, we would like to study the identifiability. We want to see that we have more and more data where can we recover this true function, or in other words, if our estimator will become the true function. And then in this sense, we want to understand the convergence or error bound of the estimator. We have to find a function space of learning. Okay, so that's the major point. And then in this aspect, as a practical point of view, we want to choose the hypothesis space, which is the basic function and the dimension of n, adapted to data. Okay, and then with these, and then we want to study then the convergence of the estimator when the data mesh refines, like the delta X refines. So this delta X refines, the mesh refines is similar to the setting of the random setting, like we have more and more samples. And in the end, we are approximating some integration over the expectation. So in this setting, we are having the mesh refines, we are using numerical integrator. So that should be easier to study. Okay. And then, as we just mentioned, as we will see later, our AN matrix, the norm matrix, will be mostly ill conditioned and sometimes singular. And also our Bn, the normal vector, have noise or numeric error in it. So regularization is necessary. Okay. So in this case, the most common regularization method is the Tikhonov or ridge regression. What we do here is we add a penalty term here. The penalty term involves two parts. One part is a regularization norm, controlling the smoothness of the function, and another is a hyperparameter, controlling strength of regularization. Okay. And in these two, then, since this is the least square problem, and this remains to be the quadratic norm here remains this one as quadratic. So we can basically solve this regularized estimator every time for each lambda, and then find a good one. So the two issues here. The first one is, given a norm, can we find a good parameter lambda? That's the optimal strength of the regularization. And this is done by the L-curve method. Basically, find a balance between the increment of the regularization norm and the decrease of this loss function. So in this case, there's a good balance is when there is an L-curve at the parameter lambda. This L-curve here, this point will be the optimal lambda. So this is a very reliable method proposed by Hansen. And now the open question in this case is, which norm should we use? And as we see, we can imagine now there are different choices. First, since we're looking at C, we can use the L2 norm, the Euclidean norm, or small L2 norm. Or we can also look at this by n as in the function space. We'll have a function space L2 rule we will introduce later. L2 rule is the option. And then if we know that function phi is smooth or in some other way, like H1 or other norm, we can also use the other norm. In our current setting, we are not assuming any information about phi. So in this case, it's become critical for us to select the correct norm. And that's our main point in our next study. The next part, we want to propose a data adaptive norm for this regularization. It doesn't work well now. Okay. Okay. So now we move on to the main part about identifiability and data, our regularization method. In this problem, we've already mentioned a few times, and to study this regression problem or learning problem, we want to find a function space of learning. And then also we want to study the function space of identifiability. Okay, the first thing start with the function space of learning, like we have in the regression. We always have x and y equal to fx, where this f will be in the L2 of the measure of x, L2 root space. So we want to have something similar. Now we look at our function phi, and then here, for example, in this operator, the independent variable here is an R variable. And then we have given data. We know that for one or two pair of data, we have limited information. We can only learn where the data give us information. So in this case, we want to quantify the information from data. That's the exploration of the variable R by data. So we introduce this exploration measure in this following format. Basically, that's where it is explored, and that's the weight. This part is the weight of the exploration. We put this as normalize it, give us a exploration measure. And once we have this measure, and then the default or ambient function space of learning is the L2 row, like in the classical learning setting. Okay. And with the expression matter, and now we can look at the loss function as from the function point of view. Right. Okay. Integrate the sixth step now. We look at this loss function. We know that what we want to do is find the minimizer of the loss functional. And in the classical sense, we would like to find the zero of its derivative. And in the functional, we look at its partial derivative. So what we do here is recall that this loss functional is quadratic in psi. So if we write this in this form, in the quadratic form, we know that we can always write this loss functional in this first quadratic term, and then also a linear term. The linear term comes from this fi and this r psi. It's the linear term. Then this phi d will be the representation part of the loss and the linear functional. So once we have in this form, now is on the quadratic form on L2 row, and then we can compute the partial derivative directly, and we see here then is this one, and then from this zero of this partial derivative we get an estimator. It's phi hat Lg inverse phi d. Okay, and since we are doing the inverse of this operator, when we should analyze this property, and it turns out this Lg actually is the non-negative compact operator, and then it will have eigenvalues converging to zero with eigenfunctions. Okay, and it could have zero eigenvalue, and it may not. So in this, that's where we are going to pay attention to. And now let's look at this inversion here. We want to decompose this phi d. We look at phi d here. It will decompose in two parts. If this fi equals to r phi 2 and then ui, and then we will see here this phi 2 will come to here because that's the quadratic part of this phi psi. And then this will get phi 2 part. And then the other part will be the error part from the noise or the numerical error. Okay. And now we put these two together. These two together will give us the inversion. Okay, that's what we see in the next slide. And in this case, it will tell us where we can identify the function. So we put it together, this one and this one together. We see that this inversion is this one. And now suppose that this phi error part is zero. And then we see that what we have, we can recover is Lg inverse Lg. Now, they cancel out, but they give us information here is that what we can identify the phi 2 is only when the phi 2 is in the span of all the non-zero eigenvalues, because this Lg inverse only works for these non-zero eigenvalue directions. So that's the function of identifiability. Only when phi 2 is inside the space, and this inversion itself can give us recover the original phi 2. Otherwise, they can't. Okay. There are two messages here. First, then this inverse problem will be ill-defined beyond phi 2. So if phi 2 have value is outside of this h, this in the orthogonal direction it has some component, then we cannot identify phi 2. And if we search beyond phi 2, beyond this h or FSOI, and then we will have many or infinitely many minimizers. So this problem is ill-defined. And now inside this FSOI, and we know that we have an inversion of a compact operator. So in this case, this inverse problem is ill-posed, and we need regularization. Okay. In this case, our regularization will have more than one task. And if we want to ensure that the learning only takes place inside the FSOI, because we just noticed, we already mentioned that this is the function space we can identify it. Outside of it, then this part is just from error. Anything we learn outside from this FSOI is just from error, because the data does not tell us any information about phi 2 in the orthogonal direction. Okay, so that's our new task for regularization. We want to ensure that the learning or the search takes place inside the data dependent of this FSOI. It's data dependent because this operator is data dependent. Okay. So the question here, how do we realize this? It turns out that there's a very nice function space in the RKHS space, give us the necessary information. And it will be this FSOI will be the closure of an HG here, the closure in the L2 row. And HG is defined by this operator in this kernel G here, or by the operator LG. And basically this G is like a Mercer kernel. And in other words, it will be this integral kernel of this LG, and then the RKHS will be the image of this square root of this LG operator. And here, this function space is a system intrinsic data adaptive because here this G depends on the operator and data. This rho also depends on the operator and data. So here the operators come from a system, a PD system or on the system. So we call it system intrinsic data adaptive. Okay. And in this case, then once we have this G or the data over there, we can compute the RKHS norm in the following format. So we can solve the eigenvalue eigenfunctions or approximate them using a generalized eigenvalue problem, and we can find the eigenfunctions. And with these eigenfunctions for any phi in this format as a change of variable, we can write this L2 norm in this form, as we know that they are orthogonal. We assume that they are orthogonal, and then our HG norm will be this way. And as we see here, then when the function outside of HG, they will go to infinity. The eigenvalue will go to infinity. Okay. And so in this case, basically we put a penalty norm here for any function outside of this this function space identifiability. Then this penalty is infinity. So that's our regularization norm. And in the end, we come to this regularization as before, and then everything will with this norm, we will constrain the learning takes place inside this FSOI. Okay. So that's the main idea here for this regularization. And the next one, we can try to understand why this data works. And the key here is this FSOI is the fundamental. If you look at the folder here is, and our inversion is essentially this one. And we decompose this phi d now in 3 parts. One part is this phi 2, and further we decomp this error in 2 parts. One is inside of this FSOI. This H is FSOI. And another one is in the orthogonal direction of this FSOI. And we know that the data, this HG norm, for the penalty term in this part at infinity. And then because in the regression, data regression, essentially what we are doing having is here, this regularization. We have an LG inverse here as the regularization term, regularization operator here. In the Bayesian point of view, this is the prior. Okay. And then by default, it will get this part away. So what we have estimated will be here. Now we're going to choose optimal lambda to balance the error in 2 parts. And then we get the good estimator. On the other hand, if we use some small L2, like the Euclidean norm of the C or L2 rules regularizer norm for regularization, what we get will be LG plus lambda C, with C being the phi G product. That's the basic function we propose, or identity operator. And in this case, we can see here, this C is not a compact operator, or it have the full space. It does not focus on the FSOI. In this case, this error, they cannot filter it out. It will remain here in this estimator. And then when we balance, find the optimal lambda, I balance the error parts, then this error will always affect the estimator. So that's why intuitively we see that this data will be better than the other two. Okay. And in practice, in general, through regression, mostly we can basically, because we are doing this matrix, and we can directly throw this part out. And even in this case, we will see that the data will give a better norm for the result. That's what we do in the numerical results. Because the data is essentially the RKHS norm, like the Mahalanobis distance for the function. Okay, so in the next part, we are now moving to the numerical examples. We are going to look at a few 3 numerical examples. I will focus mostly on the first one, and in the last 2, in the second and third one, I will briefly mention them. Okay, and what we have here is we want to learn the interaction kernel in the nonlinear operator, as we just mentioned at the beginning. It comes from near-field equilibrium, and what we want to do here is we are going to consider 3 pairs of data. One pair of data is discontinuous because here we have the one pair of data is actually discontinuous because we have discontinuity here. We are going to mention next. And in this case, we have discrete noisy data, and we want to find an accurate estimator and is a robust noise. So we are going to consider 2 types of kernels. Let's look at this one first. And one kernel is the sine function here, and with jump discontinuity, which is here, and then jump to 0, and then 0 here. Another one is the Gaussian kernel, which is a smooth function but multi-scale. Okay, and we're going to compare the small L2, like Euclidean norm regularization, and the L2 rho regularization, and compare with our RKHS. First, we notice the cyan part is the rho. When the rho is the cyan part, when it's close to zero, there's more interaction. But when the pair distance become large, there's less interaction, less density here because there's less pair distance. So that's the rho around. Now we look at this. In this one, we have the in this example here, what we have is a discrete delta x is this one, is relatively large, and we also have noise in the observation. So we can see that the estimator we have is in the sign part, we see this the dark blue one is very close to the truth up to here, and then goes to this side, it gets larger and larger because here we see the rho is very small, and then we have little data here, so we don't have much information to estimate kernel. We have large oscillations. And we compare this side when rho is larger, we have much more accurate estimation. On the other hand, the red one and the orange one have large oscillations. That's for the small L2 and capital L2, they cannot filter out of the noise. Similarly happens more clearly in the Gaussian kernel case. We can see the dark blue fits very close to the true kernel, while the red and orange, the small L2, capital L2 have very large oscillations. Okay. So that's the one estimator. We can see that the data regularizer give us much more accurate estimators than the other two. Now we move on to test the different delta x, and then we want to see if this estimator will converge. Okay. What we plotted here is we look at the red line. This is a loss value, the red lines. The dash and then the solid line, both are the loss value. And then the dash line is for the one with noise ratio is 1. The solid line is noise ratio equals to 0.1, the smaller. So we see that in both cases, the loss value here and this one here, and both converges as the mesh refines. And that's very reasonable because we are using numerical integrator to approximate the loss functions. So this follows the order there. And what we want here is we want our estimator, which is in the blue lines, the solid line and the dash line in the circle. We want them to converge. So ideally, we hope that they could converge as the loss value. We see here for RKHS, we see both the solid line and the dash line converge as the loss function. But for the small L2 and capital L2, we see here, first for capital L2, when there's very small noise, it does have converge. But when there's a larger noise, the dash line here, we see that it's getting flat. Okay, and then this rate doesn't keep the rate. And similarly happens for if we have this small L2. Small L2, when the solid line, that means small noise, is have no slope, similar to the loss value. But when there's a large noise, it gets flat. Okay, and that's the rate is slower, have a smaller rate. So it's not the conversion rate is not consistent as the noise increases. It similarly happens for when we have look at the Gaussian kernel. We see here in this case the data regulator, architecture regulator, it still converges, but then it have a slower rate. But the scale is much smaller than the other two. Okay, now we look at this one for the RKHS capital L2 here. When the noise is small, it still converges, but it have a larger scale than the RKHS regulator's estimator. And when the noise is large, then basically flat oscillates. It doesn't converge. And similarly for the capital L2, we see this when the noise is large, basically it doesn't still converge. Okay. So in this case, we see that the RKHS in this case it have a more robust convergence trend, and also is more accurate than the other two as the mesh refines. We further examine the convergence rate with different level of observation noise. The noise ratio changes from 0.1, 0.51 to 2. We see that's the noise ratio here. Okay. As we mentioned, we want a consistent rate. So we see here this RKHS, this dark blue line, have a consistent rate. And then this in this one too, in both cases, it has a consistent convergence rate. The small L2 and capital L2 we see here is basically the decays. And when this noise ratio is large, basically they almost fail to converge, as we have seen here already. This one does not get flat, does not converge. Okay, here I want to see here is this error bar is that we run 20 independent simulations and test different conversion rate. And then the error bar shows that this standard deviation of the rate. Okay, and now if you look at the Gaussian case, you may see here, okay, this part. Well, this rate seems to be larger than the RKHS. That means they are good. And we see here this part when noise is large, they're not good. Then when the noise is small, they seem to be good. And if we check this one here, and we see here in this one, we have a small noise and 0.1 is solid line. We see here this RKHS actually have a more accurate estimator than this L2. While L2 it has this one, its loop clearly will be larger. It will have a much better rate than the RKHS because the first part here is much higher than the RKHS. So the point here is for this rate, the larger rate can be deceiving. We don't trust this just large rate. We want to seek for some consistent convergence rate. Okay. So in short, in this page, what we have seen here is the RKHS give us robust inaccuracy and a consistent rate as the mesh refines. Okay. Okay, and toward the understanding of this, we can further check the L curve. As we mentioned earlier, this L curve selects the optimal parameter and the hyperparameter lambda. So in the L curve, essentially what we want to seek is such an L curve where that's the optimal lambda for the parameter. It's the as we can see here, this is the loss value with different optimal lambda and loss value, and then this is the norm of the estimator. So we see here the RKHS have the best L curve shape here and give us good the maximum curvature is very clear. On the other hand, if we look at the capital L2, then the L curve here is very unclear, and then the small L2 here is also not clear. So in this case, the small L2 and capital L2 are not as robust as the RKHS because it uses a better norm. I want to emphasize here for the small L2 and capital L2, to may have a fair comparison, I've already projected the the normal vector in the eigendirection of the operator. So it avoids the, or in other words, projecting into the FSOI. So it doesn't have this bad error to be amplified. Okay. So the second example here is we have a linear integrated operator, and it's in this format. And similarly, we see in this case it's easier. In this, all the estimator can give a reasonable estimation. And similarly, we see that this RKHS give us a more consistent rate and then the other two. And in this case, we see some others. It's interesting thing here is it have negative rate for small L2 and capital L2. That's because this, as we mentioned earlier, this different they cannot filter out the error, and they give us bad norm. And also, we don't understand one thing. We don't understand why it has a jump here when the noise goes to 0. So that's part we're still trying to understand. But overall, we see that this RKHS estimator is smaller than the other two. That means more accurate, similar here. And then the rate here is more consistent than the other two. Okay. Similarly, we have a long-local operator, as we introduced at the beginning. And this is a long-local operator here. And we have similar estimation. We are using, again, this operator, this phi here, and similar kernel sine and Gaussian. And again, we observe this more consistent rate, and we again observe another jump here. So that's another part we don't understand. But overall, still we have a more robust inaccuracy and consistent rates than the other two. Okay. So that's the main result. What we have is, in short, we have done here is we have studied the learning of kerneling operators. When learning the operator, we're learning the kerneling operators from data. And the key point here is this operator depends on this function phi, the kernel non-local, the non-local dependence. Because of non-local dependence, we have an important new issue from the class. It's new from the classical learning, is that we have identifiability issue, and there is the function space of identifiability. And then this gives us a new challenge, is that our regularization must ensure that the learning takes place inside, or the search takes place inside this FSOI. And we treat data for regression here is that it's data adaptive RKHS technical regularization to give us a good regularization. And numeric test results show that The data regularization give us robust, estimated robust accuracy and also consistent rates for different level of noise as the mesh refines. So there are many future directions. The first thing here, as natural, we have to consider now. Currently, we are still unsure of an analysis of the convergence. Like we have shown, there's some jump at the 0. And so we want to study the convergence of regularized estimator. As for delta X, another direction, as we mentioned at the beginning, is that when the data is random, we can also consider the random pairs go to infinity. So that's another direction. Clearly, this problem is applicable for general linear inverse problems with non-local dependence. So that's the many applications ahead. And the last thing I want to mention one thing here is when phi is high dimensional, it's necessary to use them. It's too high. It's necessary to use them. It's too high to use the regression, and it becomes necessary to use neural network. And I think our regularization has the potential to generalize to the neural network because we are going to regularize you with respect to the RKHS norm instead of the theta. That's a different type of regularization. And in the end, I want to emphasize the difference between the classical learning and learning kernels. So in the classical learning here is we're given xi, yi, we want to learn y equal to phi x. And in our setting, then what do we do here is in the loss function point of view, we find a gradient of the approach derivative loss functional. We're having inversion of identity operator. In that case, the FSOI is L2 row, and there's no need of the FSOI in the regularization. For our learning kernels, what we have is we have data pairs. The data depend on the phi non-locally. So we have an inversion of a compact operator. So this FSOI become crucial, and regularization must take care of this. So that's the difference. With this, I will stop here. Thank you.